In this video, we're going to go through balancing redox reactions. The essential question that we're going to be answering is how can we use the half reaction method to systematically balance redox reactions in acidic solutions. There is another method to balance in basic solutions, but this video is going to focus on acidic solutions only. So let's start by defining half reactions. These represent either oxidation or the reduction part of a redox reaction. So remember, the difference between the oxidation and reduction can be remembered using Leo the Lion says Gur. So loss of electrons is oxidation, gain of electrons is reduction. When we split our reaction into half reactions, you're going to be able to see specifically how electrons are transferred and also the changes in oxidation states. We want to make sure that we conserve both mass and the number of electrons when we're using half reactions. And there's a process, there are several steps that we're going to go through to do this. Here's an example of a redox reaction, and we've split it into two half reactions. So we have our oxidation reaction. So electrons are being lost. So you'll notice electrons are on the product side of the reaction. And then we have our reduction reaction. Reduction is where we're gaining electrons, and you'll notice the electrons are on the reactant side of the reaction. Now this is key. Notice the electrons are on the product side and the reactant side. One equation has them on the product side, one equation has them on the reactant side. This is going to be important for balancing. So let's go through the steps. So I'm going to talk through the steps, and then we're going to do two examples where we're going to use the steps to balance a redox reaction. The first step that we're going to use is dividing the reaction into two half reactions, very similar to what we did in this example right here. So we're going to divide it into the redox reaction and the reduction reaction. Sorry, the oxidation reaction and the reduction reaction. Next, we're going to balance elements other than hydrogen and oxygen. So in this example, we had copper and zinc. Everything had a 1. It was already balanced. Okay, now we're going to balance hydrogen by adding water. And when we do one of our examples, you'll see what this means. And then we will balance hydrogen by adding hydrogen ions. So adding our hydrogen ions is pretty specific to our acidic solutions. So when we get into acids and bases in a later unit, you'll see what an acid does. And this will make a little bit more sense then. Okay, next, we're going to balance the charge by adding electrons. So if I go back to my example here, you notice that the charge is balanced out. So here, this is a +2. This is essentially -2, so they balance out to 0. Same thing here. We have +2, and that's essentially -2, so the charges balance out and cancel each other out. Next, we're going to equalize the electrons in both half reactions. We want to ensure the number of electrons lost in the oxidation half reaction equals the number of electrons gained in the reduction half reaction, because they're going to cancel out when we write our equation. You should never have electrons left over in your final balanced reaction. We're going to add up our half reactions, and we're going to have just one reaction when we're all done. So again, we're going to cancel out species that appear on both sides of the reaction, such as electrons, water, and hydrogen, if applicable. Again, you should never have electrons in your final balanced reaction. Okay, so we're going to go through all of the different steps here in this reaction. So this is a redox reaction. And our first step is to divide it into two half reactions. So I have manganese and I have carbon and oxygen here. Okay, so I'm going to split it into two half reactions, one with manganese and one with carbon and oxygen. So we've got manganese and oxygen, and then I have manganese right here. The second half reaction will be C2O4 and CO2. That's our first step. Step number 2, balance things other than carbon and oxygen. So if you notice in our first reaction, I have one manganese on both sides. It's already balanced. In our second reaction, I have two carbons on the left side, but only one on the right. So I'm going to throw a 2 in front of my CO2, my carbon dioxide, to balance the carbons. Great. Now we're going to balance oxygen by adding H2O. There are 4 oxygens on the left side of our first reaction, so we're going to add 4 H2Os on the right side of our first half reaction. In our second half reaction, we have 4 oxygens here. 2 times 2 makes that 4. So our oxygens are actually balanced in the second reaction already. We don't need to do anything else. The next step, step number 4, balance the hydrogen by adding H+. So 4 times 2 gives me 8 hydrogens on the left side. We're going to balance that out by adding 8 hydrogens on the other side. Okay, here comes the confusing part. Now we want to make sure that we're balancing the charge by adding electrons. 8 times positive 1 is positive 8. This has a charge of -1. Positive 8 and -1 gives me a charge of positive 7. Okay, so I'm going to circle that. So that is the total charge on the left-hand side of our first reaction. In the second reaction, we have positive 2 for manganese, and then we have 4 times 2. Well, actually, scratch that. This whole thing right here is 0. There's no charge, it's neutral. So positive 2 and 0 will give me a total charge on the right side of positive 2. Okay, we're going to add electrons. Electrons can bring the number down, bring your charge down. It can't bring the number up. Okay, so I can't turn positive 2 into positive 7, but I can add some electrons to the left side, 5 of them in this case. Those 5 electrons will change my charge from positive 7 to positive 2. And now the left side has the same charge as the right side. All right, let's look at the second half reaction. In the second half reaction, our charge on the left side, the reactant side, is -2. On the right side, it is 0. So I can't turn -2 into 0, but I can add 2 electrons to the the right side, to turn that -2 into 0. To turn 0 into -2. Wow, I need to get some more coffee. Okay, great. All of my charges are balanced. Now, as I've mentioned several times, you want to make sure the electrons are the same number in both reactions because we want them to cancel out. You should not have electrons in your final reaction. My first reaction has 5. My second reaction has 2. You can multiply the entire reaction by a number. It will multiply every species in that reaction by that number to get our electrons to cancel out. The least common multiple between 2 and 5 is 10. So I want to multiply the top reaction by 2 to get 10 electrons. And I'm going to multiply the bottom reaction by 5 to get 10 electrons. So now I'm going to rewrite both equations. and I'm going to multiply that number through. So 2 times 5 is going to give me 10 electrons. I'll have 16 hydrogens. I'm going to have 2 MnO4. And then I'll have 2 Mn plus 2. And then 8 H2Os. In my second reaction, 5 times 1 will give me 5 C2O4 minus 2. 5 times 2 will give me 10 CO2s. And then 5 times 2 will give me 10 electrons. Okay. So again, the most important thing is making sure that the number of electrons are the same. You should have electrons in one reaction on the reactant side, as we do in the first half reaction, and then in your other reaction, you should have them on the product side. Okay, so those are going to cancel out. Okay, now we're going to write our final reaction. Anything that is on the reactant side will combine. Anything on the product side will combine. So on the left-hand side of our reaction, we have these 3 species. So we have 16 hydrogens. We have 2 MnO4 minus. And then we have 5 C2O4. On the right-hand side, we have 2 manganese ions. We have 8 H2Os. And then we have 10 CO2. There is our balanced redox reaction. That last line is our balanced redox reaction. Whew, that was a lot. Let's do it all over again. So here's another example. We're going to split it into 2 half reactions. So I've got my rhenium, and in my other one I'm going to have iodine. So I'm going to split this into 2 half reactions. Okay. The second step is to balance things other than hydrogen and oxygen. So in my first half reaction, I have 1 rhenium on both sides. In my second half reaction, I have 1 iodine on each side, so we're already balanced. The next step is going to be balancing oxygen by adding H2O. In my first reaction, I have 4 oxygens. So to balance that out, I'm going to add 4 waters on the opposite side of my reaction. In my second half reaction, I have 3 oxygens here, 1 oxygen here. So I'm going to need 2 waters on the left-hand side to balance this out. Okay, now we want to balance hydrogen by adding H+. So in my first reaction, 4 times 2 gives me 8. So I'm going to add 8 hydrogens to the other side. In our second half reaction, 2 times 2 is 4. So we need 4 hydrogens on the opposite side to balance that out. Okay, now comes the fun part. Now we are going to balance the charge by adding electrons. So we have 8 hydrogens here. This is -1. So the total charge on the left-hand side of my first reaction is going to be +7. On the right-hand side, this is 0. This is 0. So the total charge on the product side of my first reaction is 0. So I can't turn 0 into positive 7. I can't go up, but I can go down by adding electrons. So I can turn 7 into 0 by adding 7 electrons on the left-hand side, on the reactant side of my first half reaction. In my second half reaction, this is 0. This is negative 1. So the total charge is negative 1. On the right side, 4 times positive 1 is positive 4. This is minus 1. So the total charge will be positive 3. So again, I can't turn negative 1 into positive 3. I can't go up, but I can go down. We're going to add 4 electrons to the right side of our second half reaction to balance that out. All right, now our electrons, our charges are balanced out. We have 7 and we have 4. The least common multiple between those two numbers is actually 28. So we're going to want to multiply the top reaction by 4 and the bottom reaction by 7. This is turning into a doozy. So I'm going to rewrite after I distribute. So 4 times 7 will give me 28 electrons. 4 times 8 is going to be 32 hydrogens. 4 times 1 will be 4 ReO4 minus. And then on the right side, 4 of our rheniums. 4 times 4 is 16 waters. All right. In our second half reaction, 7 times 2 is 14 waters. 7 times 1 is 7 IO minuses. On the right-hand side, 7 times 1 is 7 IO3 minus. 7 times 4 is 28 hydrogens. 7 times 4 is 28 electrons. Okay, so obviously our electrons are going to cancel out. Now, we have water on both sides of our reaction. I can get rid of all 14 of our waters on the left side. I can cancel 14 of the 16, so I'm going to have 2 left. So I'm getting rid of 14 of those 16. I'm canceling them out with the other side. I have hydrogen on both sides, so I can get rid of all 28, and I can get rid of 28 of the 32, so I will have 4 left. Now I'm going to rewrite what's left over. So I have 4 hydrogens. I have 4 ReO4 minus. I have 7 IO minus. 4 Re. 2 H2Os. And then 7 IO3 minus. Wow, that was a lot of work, but it was fun. You have to admit, that was fun. All right, so that is how the balancing works when you have acidic solutions and you're balancing a redox reaction. So